Hello again. This tutorial is to look at how we can use a CCMC web tool to visualize simulation results from a solar wind model, specifically the Enlil model run at CCMC. The goals are to search the CCMC run database to find the model run that we are looking for. Look at the run parameters and the quick look feature and other aspects of the run that are available, and then look in more detail at the run through the 3D plotting tool. So to do this, we start at the CCMC, and we're going to pick a particular domain or model type, and then find a particular run for a Carrington rotation in specifically 2150. So here we are. We click on the link that takes us to the CCMC, and we go up to View Results, and there's a number of different approaches to this, but one of them is to go to the Search Simulation Results database, and it's broken down by space weather domains: the solar wind, the heliosphere, the magnetosphere, and then inner magnetosphere and ionosphere results. So if we go back to the heliosphere results, I'm not going to search. I'm going to search on for a particular Carrington rotation. So I'm going to. So initially, all columns were searched, but I know I want a particular Carrington rotation. So I'm going to search a particular column by Carrington rotation. I'm going to search for 2150. And here are all the runs done by various people for the simulation results 2150. And there are some interesting characters on here. We'll take a look at this this particular run done by this particular character, and see what we can make of it. So here's the run opening page. There's a number of different ways to view the results. First off, it tells you that it's the Enlil model, run for a stationary solar wind. That is, we're going to assume that the solution was more or less constant throughout the entire Carrington rotation. And what that means is that input to this, to run a solar wind model, you have to have already run a solar corona model. And that happens automatically at the CCMC when you ask for a particular Carrington rotation. They'll take the solar corona model and take inputs from the solar surface, in particular magnetograms, for that Carrington rotation. Run the particular solar corona model. In this case, I chose the Wang-Shili RG model, and then propagate that out into the solar wind and using the Enlil model. It gives you the grid size. It tells you that we propagated out past Mars to 2AU, and it tells you which observatory you used for the Carrington, for the Carrington map for the magnetogram for the sun, and for the Carrington map from the NSO observatory for 2150. Down the bottom here are a bunch of quick look graphs. I'm not going to click on those, but these are graphs at specific spots. For example, during that Carrington rotation, at the location where stereo A or stereo B would be, or where Mercury was during that Carrington rotation, etc., etc., all the way out to Mars, because this goes out to 2AU. We can also look at the quick look graphics for this, so I'm going to do that. This is nice because it gives you an overview of all the various run parameters that, or not the various run parameters, but it gives you velocity and density. So here's density at with Earth as a sort of fixed point. And here is also, here's pressure and then velocity, and then plots of various other plasma parameters. Similarly, you could pick stereo A, or Mars further down. Stereo B is here, etc. We can keep going down like this. Unfortunately, these plots are a little schizophrenic. Basically, it's showing you what it thinks is a time series. It's only a time. It's a time series of exactly 2 steps. And this would be nice if we were running an evolution. You get a nice movie over many, many time steps. But since we've only got 2 steps, the beginning and the end of the, it's not even the beginning and the end of the run, but the beginning and the end of the Carrington rotation, it looks a little odd. But you can still make some sense out of this throughout the, and it gives you a nice overview of what's going on. Notice down here that you've got a color map. Around the outside is mapped polarity of the magnetic field, whether it's positive or going out, or negative coming in from the sun. Those magnetic field lines are depicted, so selected magnetic field lines are depicted as dotted lines. And the current sheath crossings of these cut planes are depicted as these white lines. So notice that there's a couple of crossings here, and then one here. Similarly, on the meridial cut, there's a couple of different crossings here, and then on the radial cut, there's a crossing there. This layout is actually becoming pretty standard layout for solar wind simulation results, showing the equatorial plane, the meridial plane, and then a cut at a particular. Basically, this should be a sphere that is rolled out, cut and rolled out at a particular radius. Okay, that's the quick look data. We want to look at the 3D data results. So if you need to take a break right now or want to go back and look at anything, this is a good time to stop the video and go back and look at what we did. And if not, then continue on. Okay, so 3D data results. This is a fairly powerful tool in the sense that there's a lot of possibilities involved with this tool, but because of that, it's a little complicated and maybe a little bit complex. Whenever I go, no matter what model I'm looking at, whenever I go to this 3D web application that the CCMC has, first thing I do is I hit Update Plot. And this will take a minute, or, well, it says 5 seconds. Ah, there we go. And gives you an updated plot with the default parameters. So this is showing, this is showing density scaled with distance squared for the Carrington rotation. Gives you a color map. And this goes out to two AU for the particular Carrington rotation that we want. And it explicitly says that Earth is located at 1 AU and at 180 degrees longitude, which is, so it should be somewhere about there. Earth is located somewhere about there. Okay. There are a variety of options that we can do. So, for example, we could change the run variable. We could change the type of plot that we have, whether it's a color map or a contour plot. We could pick a cut plane. We can change the plot area, and we can adjust scales for various things. So we're going to try and do all of those things. So, first, let's look at a different variable. So this is density, right? Notice that you've got some high density areas and in red and some low density areas in blue. If I scroll down a little bit, here's the area where you change the quantity. Now there's three possibilities that you could have three different quantities going at the same time. That all depends on the type of plot you're looking at. So for example, later on we'll look at a line plot, and the line plot could have up to three different sets of data all plotted at the same time. So I'm going to change Q1 from density, the scale density, to velocity. So you've got to kind of scroll down this list. Notice that we've got velocity in the radial, the latitudinal, and the longitudinal velocity. We also have the velocity magnitude here. So I'm going to pick the velocity magnitude. There's one other, so I'm going to go back up to the top and hit update plot again. And there we are. Notice that the high density region is actually at the boundary of a high density or high speed stream. So the velocity here scales where red is really high, so 550. Yellow is probably about 400, and the blue is less than that, about 300. So the high-speed stream, the 400 kilometers per second stream, is running into a lower speed stream, and so you get in pile up there, and that's the so-called CIR, co-rotating interaction region. So that's changing the variables, or changing the type of variable that we're plotting. We also pick a different cut plane. Suppose instead of looking at, so here we are at the top, we scroll down a little bit more, we find choose plot area. I can change the whole plot region that I do, but I want to look at, instead of looking at a latitudinal cut plane that's cut through the solar equator here, I want to choose a longitudinal cut plane that's cut through the longitude of 180 degrees. So I'm going to choose that, and I'm going to hit update plot. So instead of the latitudinal cut plane, the solar equator cut plane, we now have the longitudinal cut plane going out to 2 AU from 0 AU. Well, actually, yeah, may not quite be 0. And the equator would be right about here. Earth, again, would be somewhere right about there on this cut plane. Notice that the circle on the inner boundary of this, that circle does not represent the sun. That circle represents the inner boundary of this simulation. The sun is much, much smaller than that, would be about maybe 1/10 or less than where this inner boundary is. And perhaps even 1/20. Also notice that for this simulation, the poles are actually left out, and the details of that you can read about when you read about the Enlil model. So, so this is the meridial cut plane, or the cut plane along longitude. Suppose I want to zoom in. I could do that. Suppose instead of going all the way out to 2AU, I want to go in just to, say, 1.5. So I go back down to this plot, choose plot area, and now I pick my range for my radius that I want to go out to, and I hit update plot. And now we should be zoomed in. Right. My other option, alternatively, I may want to limit the color map. For example, if you want to compare one Carrington rotation to another, this color map auto scales. You may find that inconvenient because one color map may auto scale differently from the one simulation result may auto scale differently from the other. So now we scroll down to, okay, so we're passing quantity, go to plot options. And in plot options, we can look at the color contour. We could change the color map if we wanted to. I kind of like this color map. But we could lock the scale. And let's say we want to lock it to 500 and 300. Go back up and update plot. Oops. So now we've lost some detail, perhaps, in the upper end, but we've actually gained detail in the lower end. And so we might be able to be, if we're looking for a particular feature, or we want to compare one to the other different runs, this could be useful. Alternatively, if you go back down to these plot options, you might decide that you want to choose a log scale. I haven't shown you anything with color contours or vectors yet, and that may be for another video. One of the things I do want to do, though, is look at linear plots. So to do that, we're actually going to go back. Well, let's go up to the top. We're going to scroll down and choose a plot mode. We're going to choose line 1D plot. And for that, and now we're just going to hit update, and we're going to see what happens. One of my approaches to this, when I'm doing it, is I make a few changes at a time, and I see what happens. Okay, so a few things are going on here. First off, since we had set the scale, we see that we're off scale. And notice also that there's two different axes here. So one's velocity, and we see a nice velocity plot. That goes a little bit off scale, but that's fine. The other one is density. And density, there's no way that that scale is right for density. So I'm going to go back to plot options, and I'm going to unchoose lock color range. And we're going to hit update again. Okay, so now we've got actually a pretty decent scale. You'll notice that the black is the velocity, and the blue is the density. And now by plotting the two together, we see that we have some interesting correlations. When the velocity is high, the density is low. When the velocity is low, the density goes up. However, there's still something peculiar about this. If we look at this down here, this is telling you where you are in the 3D space on a line through the plot. So this plot is the plot of these variables on a line that goes through the 3D space. But that starts at 0.1 AU and it ends at 1.5 AU, which is great, except that it also goes through a whole host of latitudes and a whole host of longitudes. So this is a line that's actually a diagonal line through the space. And I don't want that. I wanted a radial line coming out from the sun. This may even be a spiral line. I have to think about this for a minute. Yeah. And I wanted a radial line. So what we have to do is go down to the plot region again, choose plot area. And now we're going to set R2 back to 2. We're going to set the longitude to 0, both the minimum and maximum longitude to 0. And we're going to set the, actually I'm going to set that to both to 180, because that's where Earth is. Not that it matters. And then I'm going to set the latitudes to 0. So at the solar equator. And I'm going to hit update plot again. Again, making one particular change at a time. Okay, so now I'm confident that this is a line, a radial line, out from the sun, along the solar equator, roughly in the direction of Earth. And again, you see variations in the velocity and the density are correlated with each other. All right, so that's the quick tutorial on some of the features of this plot tool at the CCMC. Oftentimes for different models, even in different domains, these are very similar tools. You'll have some introductory, you'll always have this update plot button. You have some way of choosing times and the possibility of making movies. Choice of various variables. I could have put in a third variable if I wanted. Plot options that allow you to set the scale of the data that you're using or the contours. Plot area that allows you to either pick cut planes through the three-dimensional region or specific areas of the region that you want to look at. And then the list data points option where you can actually output the data. And that is the end of this tutorial.